Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at LCCC. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. This video will be an introduction into vectors, what is a vector, and then also how you go about adding or subtracting vectors. To start with, this term scalar, a scalar quantity has magnitude only. Okay, so examples are temperature, mass, speed, and time. And I have an example here of a car. The car has a speed, let's say, of 50 miles per hour. That's a scalar term. It's only magnitude of 50 miles per hour. However, a vector has both magnitude and direction. So now, if we look at this car again, we can say if we say it's doing 50 miles per hour, but it's going due east, now we're talking about its velocity. It has a scalar or an amount or magnitude, but it also has a direction involved. So some examples of vectors are velocity, momentum, force, also displacement, um, which would be, if you travel 50 feet, you need to know, did I go north, did I go south? So the displacement also is involved with direction. So if we want to add vectors, the easy situation is when they're parallel to each other. So looking at this example of an airplane here, we have an airplane that is traveling, using the green here, 100 miles per hour, let's say. Now, on the left side, what if there's a tailwind, a wind that's helping that plane go forward, and it's results in an additional 20 miles per hour to the velocity of that airplane. So these are two vectors. They're in the same direction, therefore they add. And now the plane is doing 120 miles per hour because you added the two vectors that are in parallel and in the same direction. However, if that wind was a headwind, where it's working against the direction of the airplane, now it's going to be a negative effect. And so now the plane is only doing 80 miles per hour because that headwind is slowing it down. And so if they're working together, you can add the two vectors together. If they're working against each other, you end up subtracting. And I showed two kind of ways here. You could say you have 100 miles per hour north and a 20 miles per hour south. Because south is opposite of north, you know they're going to subtract. A more common way to write this, though, is your plane is doing 100 miles per hour north. You consider that the positive direction. And therefore, the headwind is minus 20 miles per hour north, which means it's actually going south. But in this way, you have common units here, miles per hour north on both sides. However, the headwind is a negative number, and your resultant is 80. That's the more common way you would write this. But what do you do if they're not parallel? As we said, when they're parallel, they work together, you add them, and if they work against each other, you subtract them. But now if they're not parallel and they're off at angles, you need another methodology in order to work the problem. And there's actually 3 or so ways. I guess I'm going to talk about sort of 4 ways here how to go about solving problems when they're not parallel. The first method, it's not used too often, but the parallelogram method, you would take the two vectors And in this case, I'm using vectors A and B here. And you would draw them coming from the same point over here. So you would draw your vector A and then your vector B, and you would create then a four-sided parallelogram, which with these dotted lines going here. Make your parallelogram, and then draw the resultant from the starting point, as I said down here, to the end point of the parallelogram up here. And this black arrow here represents the resultant. It's the addition of A and B. This is the resultant vector that you have left. And so you can use the form of a parallelogram, and then using trigonometry from a math point of view to solve for that resultant vector, or you can graph it and then actually measure it through graphing. You will see graphing is not typically used nowadays because we have calculators and trigonometry to be able to solve these problems. But as we do here in LCC and probably at other colleges, one of your early physics labs, you will actually be asked to graph out your vectors as a way to kind of show you that you can actually just graph these with a ruler and a protractor and come up with your resultant and measure that and get your resulting vector. Now, another method here is we had started, remember the parallelogram method over here, but you could also draw A and B like I show here on the right. First draw one of them, in this case we're drawing A, and then draw B starting at the end of A, and then draw your B vector. Now, if you notice, we still get a resultant vector here from the beginning to the end point. This R, the R's here are equivalent on both sides. However, what's unique a little bit on the right side here is now you can solve the problem because you formed a triangle. So you now have this, an R, your B over here, and your A here. You can use trigonometry on this triangle in order to solve your problem. And so this is sometimes called the triangle method to use it. And again, sort of you can use graphing if you want to solve it this way also. So far we say you can use a parallelogram, you can use this triangle, or you can graph. Sort of three ways to come up with your resultant vector. But the more common method that people use is called the component method. The component method, you take each vector and you break it into its x and y components. So I'm using here as an example this vector A. It has a magnitude of A and an angle off the x-axis of theta. So we would take that situation and we would break it into components. So that one vector A, we would break it into components, a component in the x direction and a component in the y direction. So this is similar to the triangle method. You've now taken this one vector and broken it into two vectors, ax and ay, one along the x-axis, one along the y-axis. Once you do that, now if we move down here to the lower left, from a trigonometry point of view, now you can write some equations. You know that ax is also going to be equal to the magnitude A of the vector times the cosine of theta. That is the distance of ax. Ay is the magnitude A times the sine of theta. And also, because of that, because of Pythagorean's theorem over here, I'm not going to try to spell that, you know that a squared is equal to ax squared plus ay squared. And with trigonometry, you know tangent of theta is going to be ay over ax. So by breaking A into components, you've created a bunch of equations now that could help you in your problem solving later, because occasionally you will get, maybe they'll give you AX, but they maybe to give you AX and AY and you're solving for A. And you can use these equations to get there. Or maybe they give you AX and a theta, and then you can solve for AY or A. So you have a bunch of equations with this component method that you can utilize for problem solving. And here's a quick example of how you could take that two-vector problem where we have two vectors, v1 and v2, coming together, and you're looking for your resultant, which is your vector v. Now I said you could use the parallelogram method, you could use the triangle method, you could also graph this, but in the component method, you would take each vector, so you take v1, break it into your v1 x direction, v1 and y direction, do the same thing with v2, v2x and v2y, and now you can get the overall vectors vy and vx, which represent sort of the components of the overall resultant vector v. And you have now another set of equations. You know that this vx is actually the sum of the x directions for the two vectors that make up your resultant. And y is your y directions of those two vectors added together. And in this way, if you have 2, 3, 4, however many vectors you have involved, if you're looking for the resultant, you can break all the vectors into their x and y components, sum them all together, and get your overall vector, your y direction and your x direction vectors for your resultant vector, and solve your problem that way. So that's how a component process works, and as I said, it is the most common way to go about solving your problems in physics. Thank you.